let's get moving. If you didn't pick up your exams, I brought them in. I'll bring them in on Monday. So anybody didn't pick up the exams can do so. Question and answer today, 4 p.m. same place. And I'm not sure why there's some confusion that I posted the solutions to exam 3 on Lima. So anyway, just thought I'd bring that up. Let's continue our discussion of the chemistry of aromatic heterocycles. So last time we mentioned that furan, but also thiophene and pherol, although they are aromatic, they also behave like diene. If the aromatic stabilization is not so huge, they do the characteristic diene reactions, which are Diels-Longo cycle addition and conjugate addition reactions. And so these kinds of this kind of chemistry is associated with conjugated hexadiene or with cyclohexadiene or butadiene, and yet we see the same kinds of reactions taking place with an aromatic heterocycle because the aromatic stabilization is not all that great, actually. And then the last thing we talked about, the very last thing, was the side chain oxidation process. Notice that I'm showing oxidation of an aldehyde to carboxylic acid and alcohol, either to an aldehyde or to a carboxylic acid. The corresponding oxidation of a methyl group is a little bit hard to do in this case because the conditions that we need are extremely harsh, and typically the aromatic ring gets zapped if you do that. So now let's take a look at pyridine chemistry, which is a little bit weird, and we can understand it based on first principles. But the first time you see this, it looks a little bit strange. And so electrophilic aromatic substitution for pyridine is technically not all that easy to do. So you'd say, well, what's the difference? I have benzene. I just take one of the carbon atoms in the benzene ring, put a nitrogen in its place. Is that really such a huge change? The answer is yes, it is, because the nitrogen atom is basic. And so all of these electrophilic aromatic substitution reactions that we've discussed take place in the presence of either a Lewis or Bronsted acid. And so the presence of that lone pair on the pyridine means that the first thing that's going to happen for anything else is that lone pair on pyridine is going to engage the acid. So in this case, it's going to be Bronsted acid. These are the conditions, remember, for aromatic nitration. So the first thing that happens is proton transfer. Now, how do I know that? Well, because proton transfers are fast and they occur with low activation barriers. So we can be absolutely sure that when you throw pyridine into this mixture, that's what you got. Now, at this point, look at what you want to do. You've got an aromatic ring that already bears a positive charge. And if I want to do an aromatic nitration, I've got to stuff a second positive charge into the same ring. Not good, because now I've got a doubly charged, doubly positively charged species. And that's going to cost me quite a lot of energy. And that's why this process is not easy. Now, to compensate for that, what one typically does is one uses, really forcing conditions. But under those forcing conditions, it's sometimes difficult to control the number of substitution reactions that take place. So in other words, you do one substitution and then you do a second one sometimes. So getting the monosubstituted is kind of hard. Now, you notice that I've shown nitration taking place at C3. So we start counting at nitrogen being 1, 2, 3. So C3 is right there. And the reason for that is the same as ever. I need to write the resonance structures for the charged intermediate that I get, and then based on what I see for those resonance structures, I know whether or not C3 or C4 and C2 substitution is preferred. So if it's at C3, I end up with these 3 resonance structures. I haven't shown the double charge, just to keep it simple. So I get 3 resonance structures for C3 substitution. On the other hand, I still get 3 resonance structures for substitution at C2 or C4. C2 and C4 are going to be equivalent. I'm just showing C4. So I still get 3. However, this one is going to be absolutely lousy, which means that it doesn't contribute overall to the structure. And it's bad because the nitrogen atom, not only does it have a positive charge, so positive charge on electronegative atom, but it doesn't have an octet either. And so remember, the only time that we see important resonance structures where you put a positive charge on nitrogen, positive charge on oxygen, is when they have complete octets. Here, this does not have a complete octet. For purposes of octet rule, this has 6 electrons. And so this is an electron pair short of octet. And so what that really means is that this resonance structure can be ignored. And because it doesn't really, it's too high in energy. So what that means is that you only have 2 resonance structures for C2 or C4 versus 3 for the observed C3 attack. And so when you do electrophilic aromatic substitution on pyridine, C3 is where it happens. It doesn't happen at anywhere else. You can of course see an easier reaction. In other words, reaction under milder conditions if the pyridine ring is activated. And so here's a case of a pyridine ring which has activation, and sorry, somebody left this board in a bad place. And so, in this case, the pyridine is substituted for electron-releasing methyl group, so the substitution is going to be easier. In all cases, it's the tiny amount of the uncoordinated pyridine that's going to react, and so you typically don't get that doubly substituting, but it also means that in strong acid, you just don't have much of the aromatic electrophile. Now, the question, of course, is, are we stuck with electrophilic aromatic substitution in C3? In other words, let's just say that I have, somebody pays me a lot of money to make a C4, or as we'll see later on, a C2 substituted pyridine. And so how do I do it? And is there a way to get around this? And it turns out there's a very clever way to get C4 substitution, and that is you oxidize the pyridine ring first. Now, amines undergo N-oxidation. And this is a process that takes place spontaneously in air. We live in an oxidizing milieu, and so this reaction will take place all by itself if you wait long enough. So if you have an old bottle of triethylamine, for example, you have a significant fraction of trimethylamine N-oxide present. And so what does trimethylamine or triethylamine N-oxide look like? Well, it looks the same way. It just has a nitrogen-oxygen bond, and that bond is polarized like so. So this would be triethylamine N-oxide. So in order to convert this back to triethylamine, you have to reduce this bond. And so because the amine is oxidized, of course, going in the reverse direction is going to require a reduction. If you have an old bottle of triethylamine, typically what you do is you distill it from zinc metal. And zinc and low valent metals, zero valent metals, are reducing agents. And so the zinc is converted through a fairly complicated process, I assume, to zinc oxide, and you end up with triethylamine that is uncontaminated by triethylamine N-oxide. Okay, so that was just a little aside. So it's easy to convert pyridine to pyridine N-oxide. And the way to do it is to use, if you're not really willing to wait for a long time, just throw it into hydrogen peroxide, and that works really well. Now, when you look at the structure, what you want to think about is phenol. Okay, so once again, if I just ignore the fact that this is nitrogen and think of this as being a carbon atom, then this looks just like phenoxide. So phenoxide and pyridine N-oxide look pretty much the same. Now, it's not just the appearance that we're interested in, but of course the resonance structures are going to be pretty much the same as well. What do we know about phenol vis-a-vis electrophilic aromatic substitution? Well, we know it's highly activated, right? And we know that phenoxide is even more highly activated because you have a full negative charge on the ring. And so what this tells you is that the pyridine N oxide should be a pretty hot nucleophile to react with electrophiles like NO2 plus or whatever. And that's the case. And so what you can do is you can do these substitution reactions of the pyridine N oxide. Again, I mean, this takes a little bit of heating for a while, but the yield is very good. And notice that you get exclusively substitution at C4. Now, whenever you play this little game of changing the starting material, doing a reaction, and then saying, well, I've got it to work. The question you always want to see is that, yeah, but can you convert it back into the original functionality? In other words, we started with pyridine, then we converted to the N oxide. We did the chemistry on the N oxide. Is there a way to go from N oxide back to reduced pyridine? And yeah, lots of ways. You can either do it catalytically, but notice catalytically reduces the nitro group as well, or PCl3 will also do it, and there are other ways to reduce that NO bond. Now, the reason that you get C4 substitution here, not C3 or not C3, is not that hard to see. If I show the resonance structure for nitration, I'll have this, right? And so one of the important resonance structures that I'm going to get for this is this one. Plus on the nitrogen, this is a double bond. Of course, there are others, but this is an important one. Well, why is this the important one? I mean, I can delocalize that charge. I have other ways to delocalize that, but this is the important one. Why? Yeah, everything's done like that. So, yeah, it's the same. I mean, it's the same stuff we've been talking about. So that's why I said that even though this chemistry looks a little bit different and maybe a little bit weird, we can understand what's going on based on first principles that we learned way back when we talked about electrophilic aromatic substitution. And so it all goes back to taking a look at the stability of the intermediates. Now, things get really weird with the Chichi-Babin reaction, named after a Russian who figures this out. Okay, now take a look at this. This is really weird. You take pyridine, you treat it with sodium amide. Now, sodium amide is amide is the conjugate base of ammonia. It's a very strong base, pKa of 35 or something for ammonia. So that tells you that this is a very strong base. Now, this is acting not as a base, not pulling a proton off. It's acting as a nucleophile, and it is substituting that red hydrogen atom. And so this is very strange because it looks as if we don't have a leaving group here. I mean, there's no leaving group at the alpha carbon atom, and yet we're getting a substitution of a hydrogen by NH2. Now, this is a nucleophilic aromatic substitution reaction, right? Because we have an aromatic ring, we've got a nucleophile, we're getting a substitution. But nucleophilic aromatic substitutions don't look like that. They usually look like this. When we had a nucleophilic aromatic substitution, we had a halogen. It worked better with a fluorine than a chlorine because the carbon-halogen bond is not lost in the rate-limiting step. And then, in order for this reaction to work well, I had to have at least one strongly electron-withdrawing group, either at the para or at the ortho position, and preferably at both. So this would be a very good substrate for nucleophilic aromatic substitution. So normally, this is what happens. You get nucleophilic addition, And then you can see what the nitro group is doing. The nitro group is stabilizing the negative charge that you get when you add your nucleophile to the aromatic ring. You have a bunch of resonance structures. I won't write them, but you can figure out that this negative charge is now stabilized by both nitro groups. So you have all those resonance structures, and then in a second step, not in the first step, but in the second step, you end up expelling the chloride and getting chloride as your leaving group and the substituted aromatic ring. So this is how we learned nucleophilic aromatic substitution to take place way back when. So this is a normal kind of a nucleophilic aromatic substitution reaction. Now, notice that I have a chlorine or a fluorine or some kind of a leaving group there, and that you get a two-step reaction. You get an addition step, which is slow, and then an elimination step, which is faster. The addition step is slow because that's the step in which you lose aromaticity of the ring, and then the elimination is fast because you end up restoring the aromaticity. Fine. So how does this work here? I don't have a leaving group. Well, let's take a look. That's why I said this is a strange reaction. So you get addition. You can delocalize the negative charge onto nitrogen, which is good. That's why addition takes place here. And you end up with these three resonance structures. But then, of course, in the second step, you have to spit out not chloride, but H minus. Boy, that's kind of strange. We've never seen hydride acting as a leaving group before. Now, having said that, probably we have something that's a little bit more nuanced than this. Probably what we have happening is that, if I write this structure here, you probably have some partial, because the negative charge is going to be close to the sodium. There's probably some partial bonding in the transition state, I would imagine, from the, as you start to break the carbon-hydrogen bond, you probably start to make the sodium hydride bond. So I don't think you ever end up with a naked H minus, a H minus in the absence of a sodium plus. But nonetheless, this is a very strange reaction, not something we've seen before. Now, let's take a look at something in pyridine. I'm going to show this again, but let me just draw pyridine for you. And let me highlight one of the, let me highlight this part here, okay? Okay, so if I look at this red part, what does that look like? Let me just redraw the red part. Have you ever seen anything like that? You know, where you have a bond here too. What's this functionality called? No. Terpenes are compounds that have repeating units of that. This isn't a terpene. I see why you say that, but no, terpenes are all carbon, no nitrogen. What carbon-nitrogen double bond, do we call that? Yeah, I heard it. It's an imine. Okay. So imines have a carbon-nitrogen bond. That bond is polarized in this direction again, right? Positive end on carbon, negative end on the electronegative nitrogen atom. So imines are the nitrogen equivalent of ketones and aldehydes. So this is not an imine, but boy, it sure has got an imine function embedded in there, and it has imine-like reactivity. And so let's recap this. So the addition step that we saw for the Chichibabin reaction should look a little bit like a nucleophilic addition to an imine. In fact, it should look a lot like that. And so you think of a nucleophile adding to an imine here to generate the tetrahedral intermediate, and then think of this reaction taking place. This is something we've seen before. We've seen imines reacting, for example, with hydride. And so this process and this process are clearly related. And it also should remind you, because if I substitute nitrogen for oxygen, it should remind you of the nucleophilic addition to a carbonyl group. And so what emerges from this picture is that this part of pyridine looks kind of like a ketone. where you have a carbon and then an electronegative atom. And so you can expect to see nucleophilic addition reactions taking place where I'm pointing. We're going to see other ones too. So in all cases, the addition takes place to a polarized C heteroatom bond, and that's the key thing to recognize. So the common feature between pyridine, ketones, aldehydes, imines is that you have a carbon, either oxygen or nitrogen, but carbon electronegative heteroatom bond. Back to the mechanism now for the reaction we're talking about. The next step is this loss of hydride. Very, very strange. I suspect you never get free hydride. Sodium is right there, so as you're breaking the red bond, you're probably associating that hydride with sodium. But of course, you now have a very strong base, and you've generated a primary amine. So you know what's going to happen next. This hydride is going to react with one of those hydrogens, because hydride is a much stronger base than ammonia. And so you will generate H2 gas and the sodium salt of the 2-aminopyridine. The sodium salt of the 2-aminopyridine is, you guessed it, resonance stabilized, and so that's shown here. So this is a stronger base than the primary amine. So you form hydrogen gas. Hydrogen gas bubbles out of this, and then that gives you the sodium salt here, and then the negative charge is delocalized. Then when you work this reaction up with water, this gets protonated by water. You get sodium hydroxide and 2-aminopyridine. So this is unique. We've not seen anything like this. We've never seen hydride act as a leaving group. And so, yes, this is something new that we've not seen before. Now, it turns out that this process is not limited to NH2 minus acting as a nucleophile. In other words, you can use carbon nucleophiles and get the same kind of chemistry, although the yields usually are not very good here. 50% is about what you can expect. But look at what happens. Phenolithium, so think of this as phenyl minus, adds to the imine double bond and then expels H minus. So in this case, because you use lithium, not sodium, you end up with lithium hydride, not sodium hydride. And so this process also works. And the question, of course, that you might have is, can't we make this process a little bit easier to do? These reactions, you've got to heat them up, or they're not very fast. And of course, hydride, as you know, is a lousy leaving group. So just about anything is going to be a better leaving group. Even methoxide is going to be a better leaving group. So old methyl. But if you really want to make this, if you really want to soup up this process, what you do is put a chlorine here. And so now when you do an addition elimination, this is another nucleophilic aromatic substitution reaction. Now it looks a little bit more like the one I showed you with the nitroaromatic, because I have a leaving group and the negative charge, you can imagine, is going to be stabilized by the nitrogen atom. And so methanol, or methoxide and methanol works really, really well. You get, mild conditions, you get good yields, because this reaction has a lower activation barrier. Now, what did we say about, just moments ago, about purity? Well, we said that this should remind us, this part of the molecule should remind us of an imine or an aldehyde, okay? But if I put a chlorine here, imagine this being a chlorine, then imagine a chlorine being there, right? So if I put a chlorine at the position of pyridine, then it's going to look like this species, but with a chlorine substituted there. What do we call that? We call that an acid chloride. And so if we compare this structure to that one, we're comparing an aldehyde to an acid chloride. I'm reminded of the bar in Manhattan. But she escaped before. Okay, so this looks kind of like an acid chloride. And in fact, the reactivity is going to be much, much higher with the chlorine than with the hydrogen. And so if you have access to the 2-chloropyridine, of course you're going to use the 2-chloropyridine for nucleophilic aromatic substitution. So you know, at the risk of sounding repetitive, you can relate a lot of this chemistry to things that we've already seen before, and you should. The one that you can't relate is that loss of hydrogen. That is new. Now, once you form the 2-aminopyridine, this can be diazotized, and then you can do all the kind of diazoniamine chemistry that we saw before. And remember that we saw diazoniamine chemistry in the context of what? Of electrophilic, well, we call it electrophilic, yeah, I guess electrophilic aromatic substitution, we'll call it that, but of course the mechanisms for the diazotized, you know, for the Sandmeyer reaction, those ones where you use copper salts and whatnot, those mechanisms are typically radical mechanisms. We didn't talk about the mechanisms. So here, you can do the same chemistry, radical mechanisms. We don't need to talk about it, but just be aware that this amino group is a precursor for very, very useful intermediate here that can be functionalized in all the ways that we've seen. Now, diazonium salts, remember, were kind of interesting for us for another reason, that we could convert them to alcohols, or we could reduce them too. Reduction is not particularly useful here, but hydrolyzing it to an alcohol is, because the 2-hydroxypyridine that you get out of there is the enol form of 2-pyridone. And so where have we seen this kind of situation before? You know, where we have something like this. Well, think of phenol, and think of a keto form of phenol. Well, you know that this is essentially not there, you know, because phenol doesn't, you know, you don't have any double bond character there. You have the aromatic ring, but in pyridone actually you have a lot of this in equilibrium. So the keto-enol equilibrium overwhelmingly favors phenol, but with the 2-hydroxypyridine it doesn't overwhelmingly favor the 2-hydroxypyridine. You end up with, I forget what the equilibrium is, but it's roughly 1-to-1, maybe 2-to-1 or something. And so there's a lot of this stuff around. Now, why should that be? Why should this be different? Well, think of what we said about carbonyl stability. Which carbonyl group is more stable, ketone or amide? Amide is way more stable than a ketone or an aldehyde. And so that is consistent with what we see here. It's consistent with seeing a lot more of the carbonyl equilibrium product in 2-hydroxypyridine than in phenol. So unlike phenol, there is a lot of 2-pyridone in equilibrium. Oh, and by the way, yeah, that's going to be true regardless of solvent. So you don't need any kind of hydrogen bonding solvent or any kind of polar solvent to stabilize this. You get a substantial amount of that regardless, which is kind of interesting. Now, so why is that? Well, because there are two competing effects, right? You have the aromatic stabilization that would suggest that it always is 2-hydroxypyridine, but then you have, competing with that, you have the stabilization of the amide carbonyl. And so it just turns out that when you have an amide versus the aromaticity, and the aromaticity of the pyridine is a little bit less than for benzene, it just turns out that the equilibrium favors the pyridone to a larger extent. Now the pyridone can be converted to chloride or anything you want, and this reaction kind of should remind you of converting an acid to an acid chloride. Why? Well, because if I think of the 2-hydroxypyridine equilibrium species, then that's going to look very much like a hydroxy group here. It's going to look sort of like that, and so you can see the analogy between the chemistry that we learned for converting a carboxylic acid to carboxylic acid chloride, and this chemistry converting pyridone, or if you prefer 2-hydroxypyridine, to the 2-chloropyridine. So the same kinds of reagents that are used for this chemistry can be used for this chemistry. Okay, so now the next thing you might think of is that, well, we saw, if we have 2-chloropyridine, we can do nucleophilic aromatic substitution really easily. What about 3-chloropyridine? So let's just say that I have, somebody gave me, forget about how we got our hands on this, but somebody gave me a sample of 3-chloropyridine. So if I do a nucleophilic aromatic substitution here, addition, elimination, and so on, the question mark is, can I get a nucleophile to do this kind of chemistry? Does this work? And the answer is no, it doesn't. And the reason it doesn't work is because you never end up delocalizing the negative charge onto the nitrogen atom this way. And so remember why it works so very, very well at C2. The reason it works so well at C2 is because you end up placing the negative charge on the nitrogen atom. And so, where is it? I don't see it. But so when you do nucleophilic aromatic substitution at C2, the nucleophile adds here, and then the negative charge is on the electronegative nitrogen atom. And so you end up generating right away a very stable intermediate, this one. You can't do that when you add the nucleophile at C3. C2 works, C3 does not. And so this probably should not surprise you in any way. So if I do the nucleophilic addition at C3, the negative charge delocalized as shown, but it never ends up on nitrogen, and so the activation barrier for this process is much higher than for C2 substitution. So 3 substituted pyridines, in other words, pyridines substituted with the 3 chlorine and fluorine, not very reactive at all. They don't undergo nucleophilic substitution. Okay, so we saw one trick for accelerating the nucleophilic aromatic substitution at C2. What was that trick? Well, you put chlorine at C2, and that ends up looking a lot like an acid chloride. You get a much better nucleophilic aromatic substitution. You get the addition reaction. Now it eliminates chloride, a good leaving group. Turns out there's another way to game the system too, and that is to use a pyridinium salt. Now, what did we say about amines in general way back when we talked about amines? We said that amines are characterized by having that non-bonding electron pair on nitrogen. That non-bonding electron pair on nitrogen can do one of 2 things. It can either act as a base, in which case it bonds to a proton, or it can act as a nucleophile, in which case it makes a bond to a carbon atom. And so I can allow pyridine to react with methyl iodide in an SN2 reaction to give me an N-methylpyridinium iodide. These are stable compounds, typically crystalline, and these reactions proceed in very high yield. So now, when you look at this, the electron pair on nitrogen is engaged in a bond with a carbon atom. And so what this should remind you of, it should remind you of an activated carbonyl, right? Because you have in both cases, you have, so if you think about the pyridine, and it doesn't have to be methyl, obviously. You have this species, and what that means is that this carbon atom, that one right there, is now activated the same way it would have been activated in an aldehyde if the aldehyde had been protonated, say. Okay, so you have the heteroatom protonated, that amplifies the reactivity of this carbon atom, just as we've seen many times before. And it doesn't have to be a proton, it could be a Lewis acid, Bronsted acid, it makes no difference. But as long as the carbonyl is protonated, then this carbon heteroatom bond is more reactive to nucleophiles. And so that's what we've done by forming the N-alpha-pyridinium species. What we've done is we have increased its reactivity towards nucleophilic attack at C2 or C4, but typically it's C2. So you can now do the reaction that you saw before with just pyridine, but under milder conditions. Well, okay, but you don't get the same product, right? Because now I have this N-methyl group. That N-methyl group is sticky. In other words, there's really not an easy way to cleave that. Turns out there are other ways, there are other groups you can put on the nitrogen that can be cleaved easily. So this is a useful general technique. We don't need to talk about the other groups that we can put there, but this technique does work. But so you can cleave that, but of course you also don't have a pyridine anymore. You end up, because you don't end up expelling the hydride, you end up with a reduced pyridine. It turns out that you can, if you could cleave the N-methyl group, then there are ways to oxidize it back to pyridine. So this trick works in general. It's a good trick. You can use much weaker nucleophile, weaker bases than this. You can do nucleophilic addition of hydroxide, and then you can oxidize this to the N-methylpyridone. So all of this chemistry, and you don't have to, don't memorize these reactions. Just understand what's going on from a framework of what you learned before. This is a secondary alcohol. Secondary alcohols get oxidized. And so you can think of the oxidation process as one that removes the elements of H2 from here to give you the carbonyl. The chemistry with the N-oxides is also interesting. Notice that we said that N-oxides can be used for electrophilic aromatic substitution, but look at this. They're also useful for nucleophilic aromatic substitution. And so when you do a nucleophilic aromatic substitution reaction, now all you need to do is dehydrate that, and you have it. So these N-oxides, as you can see, are going to be useful. They can do all kinds of stuff. You can use them for in place. So they're sort of like a surrogate of phenol. So here's what we talked about, where you treat the N-oxide with an electrophile, NO+, and then you end up reducing that. Or you can take the same N-oxide, instead of using an electrophile, a cation, you can allow it to react with a nucleophile. Now in this case, you end up with a different species, but you can eliminate the elements of, well, not water, but acetic acid here, and end up with the C2 product. And so let's take a look at the mechanism for this particular reaction, just so we can understand what's going on. So you have a negatively charged oxygen atom, you treat that with acetic anhydride. What do you suppose is going to happen? I'm just going to put this as phenol. What do we know about this carbon atom? This carbon atom is electrophilic, right? So I'll get a tetrahedral intermediate, which I won't show. That tetrahedral intermediate, in the second step, will expel acetate. So this is two steps here. And I end up with acetate as my byproduct, just as we've seen before. Okay, now a very weak base can pull that proton off and expel acetate. And why is this process so easy? Well, because it restores the aromaticity to the ring. And so you end up getting your pyridine ring back again. You end up with acetate as your leaving group. And from here, you end up with we guessed it, acetic acid. And so this process works really, really well. Now, that makes use of the pyridine N oxide. So you see the pyridine N oxide is kind of a chameleon. It can act as either a very good nucleophile or a much better electrophile than pyridine. And it depends on whether you're allowing it to react with something like NO2 plus, a good electrophile, or whether you're allowing it to react with phenyl minus, a good nucleophile. But in all cases, the reactivity follows from first principles, and that's the take-home message. You don't have to memorize, oh, it does this under these conditions. No, just understand the mechanisms, and then it all falls into place nicely. Okay, so now, what were the other reactions we saw when we discussed benzene? Well, we saw electrophilic aromatic substitutions, we saw nucleophilic aromatic substitutions, and we saw side chain reactions. What kind of side chain reactions did we see when we talked about benzene? Well, there were two kinds. The one kind was typified by, we've heard this before, by radical generation, that you can use a radical chain mechanism to generate a stable benzylic radical, and then benzylic radicals can react in a chain to do, say benzylic bromination reaction. That's one side chain reaction. The other side chain reaction was a vigorous oxidation process that gave rise to carboxylic acids. And so these were the two typical side chain reactions that we've seen. Well, it turns out there's a different kind of side chain reaction that takes place with pyridine, but it makes use of, well, I shouldn't say makes use, it is explicable if we think of, and this can just be an R group, if you think of the similarity of the pyridine with a methylpyridine with a methyl ketone. So if I think of the similarity of these two structures, and by similarity not just structural but in terms of reactivity, then if I look at this methyl group, of course it looks like that methyl group. This methyl group, now we go back to carbonyl chemistry. When we talk about carbonyl chemistry, I said that, way back when, I said there were two kinds of reactions that ketones and aldehydes undergo. And we've seen one of them. Okay, so one of the reactions that ketones and aldehydes undergo is that they react with nucleophiles at this carbon atom, right? We just saw that here in spades. There's another reaction that they undergo. And the other reaction is that they, either through their enols or through their enolates, that they are nucleophilic species which react with electrophiles. Okay, so two kinds of reactivity for the ketone. Nucleophiles add to the carbonyl, and then the enol or the enolate reacts with electrophiles. Well, we saw nucleophilic addition there. We just saw it on the pyridine, we saw it on the chloropyridine, we saw it on the pyridine N oxide. Now the question is, if I treat this with a strong base, can I pull one of those protons off and form this CH2 species, which looks just a little bit like that enolate, right? Because here I have a carbon-oxygen polarized double bond, here I have a carbon-nitrogen polarized bond. So I would expect this to be sort of like an enolate. Another reason it's like an enolate is because of the resonance structure I can write for this. Recall that I can write a resonance structure here that looks very much like the one that we saw for the enolate here. And this should be a nice resonance structure because the negative charge is on the electronegative nitrogen atom. So that kind of reactivity also can be seen for side chain reactivity for pyridines. But you do need a strong base, and you need butyllithium. Now, could we have used butyllithium as the base to deprotonate the ketone? So I just showed you the ketone deprotonation. Well, I didn't show you the deprotonation. I showed you I showed you ketone and I showed you enolate. How did I pull that proton off? Well, I didn't tell you. But could I have pulled it off with N-butyllithium? Could I have used N-butyllithium to abstract one of those protons to form that enolate? No. Why? Yeah, because butyllithium is a good nucleophile. It's just going to form the tertiary alcohol. You got it. So to form that enolate, what do I have to use? I have to use a strong non-nucleophilic base. What's the archetypical strong non-nucleophilic base? It's LDA, right? Lithium disopropylamide. This negative charge got a little too big. So LDA is your non-nucleophilic, one of the non-nucleophilic bases. Okay, so that is different, right? Because the electrophilicity of this carbon atom is not nearly as high as a ketone, and so I can use Bewley to pull that proton off. And so this now is a very good nucleophile, and it should remind us of enolization. There's LDA again, pulling that proton. Why LDA? Well, because I can't use butyllithium on the ketone or bad things will happen. Now, like enolates, just like enolates, these carbanions are nucleophilic. And so I can trap them with all manner of electrophiles. I can trap them with aldehydes, I can trap them with ketones, I can trap them with esters, with, you name it. And so this kind of reaction takes place very, very nicely. And the interesting thing, of course, is that if I convert this to the pyridinium ion, now the acidity of that proton has gone way, way up by, roughly 1 million, well, more than 1 million times. And so now I can pull that proton off with hydroxide. And the reason for that is because the enolate, the enolate structure is actually neutral now. So once I pull that proton off, I end up with a neutral species. By the way, what is this functionality called? Here, forget about the dying. Okay, what do we call that functionality? Have we ever seen something like that before? Have we ever seen a species that looks like? So I'm pointing to this, right? Have we ever seen something that looks like that? And does it remind us a little bit of this is an enol, right? This is an enamine. So en there, amine there, en there, ol there. Both of these species have similar reactivity, right? They're nucleophilic on carbon. Why? Well, because they react like this with electrophiles. And so both of these species will react with electrophiles. And you can think of this as being the conjugate acid of the enolate, which it is. Now, if I compare this species with that, you can see that this is an enamine, and so it is going to be nucleophilic on carbon. And so the same kind of chemistry that you see for the enolate, let's just call this an enolate, you can see with the enol. So this is the enamine, let's just call it an enol. So it all should remind you of what? Of chemistry that we learned when we talked about ketones and aldehydes. And it's not really substantially different. The only difference was that loss of hydride. That is completely unprecedented. We've never seen anything like that. Everything else that we've talked about in this chapter has been covered in earlier discussion. Slightly different, I agree, but principles all the same. Please try to make the effort to see that connection, and this will become a lot easier. What you don't want to do is you don't want to look at each one of these reactions and try to memorize it. That won't work. Okay? So just look at the mechanisms and try to relate it to the earlier work, and then it will make perfect sense to you. So what we're going to do on Monday when we meet is we're going to talk about vitamin B6 and some of the chemistry that is associated with that. It's going to look an awful lot like the mechanisms that we talked about when we talked about ketone chemistry. For those of you who walked in late, there's a question and answer this afternoon.